Welcome to SOFiSTiK online documentation. In this video, we'll cover the first step in the general workflow for seismic nonlinear time history analysis. We will show how to model a plastic hinge for cyclic loading and how to assign its performance categories. To define such a hinge, two elements are required. A backbone moment rotation curve, which defines the sectional capacity, and a model that describes the cyclic behavior of the hinge. Here, we will use the modified Takeda model, which is particularly suitable for reinforced concrete structures. It defines rules for loading and unloading of the structure, allowing control over the unloading via the exponent alpha and the reloading via the factor beta. For more details on the modified Takeda model, please refer to the FEA bench manual, where you will find a section describing its properties. The modeling procedure starts with defining the materials and cross-sections of the bridge pier. We use C35-45 concrete for the header beam and B500 reinforcing steel. Additionally, we defined a new material for confined concrete based on C35-45 with manually specified stress-strain relationship. To ensure that this material is used for the plastic hinge, we modify the stress-strain curve of the serviceability limit state. The header beam uses a standard rectangular cross-section, while the section of the confined concrete is modified in SOFi+. We proceed to calculate these cross-sections. Both of the cross-sections are displayed in the report, where we can see that the confined cross-section has one material on the inside and another concrete material on the outside for the cover. Before defining the plastic hinge, we start by globally defining performance categories based on strain levels, which we will later use to assess the structural performance. This is done in the plastic hinge performance categories task. We define separate categories for the concrete and reinforcement. Each category includes 3 performance levels: fully operational, operational, and life safety level. Later, we will assign these specific strain categories for each material within the plastic hinge. Next, we add the plastic hinge task. This requires adding a new corresponding workflow task. This is because the output of the cross-sectional analysis is a workflow representing the plastic hinge behavior. In the plastic hinge task, we begin by selecting the cross-section to be analyzed. We use mean material values, ensuring that the serviceability stress-strain relationship are applied. For the concrete, we select the predefined confined material law with 6 per mil strain for the yield strain and 10 per mil strain for the ultimate incompression. For the reinforcement, we select the material B500 with a yield strain of 2.5 per mil and an ultimate strain of 50 per mil. In the plastic hinge tab, we are able to name our hinge, and we use the name Takeda implicit hinge. The Takeda model supports bending type of hinges without the interaction of the normal force. This means we can only use bending type of hinges for one level of normal force. In our case, we will specify MY hinge and set the normal force to minus 5,500 kilonewtons. This is based on the structure's dead load, as we will see it later. Please note that this may be an iterative step. The normal force may need to be calculated first through linear analysis and then used in the hinge definition. The plastic hinge length is calculated as 71 centimeters based on the Eurocode recommendations. These are given in the commentary over here. We use Caltron's idealization of the moment curvature, and the material type is set to modified Takeda models. And for this example, we leave the loading and unloading factors to 0. In the performance limits tab, we describe the performance levels by specifying strain values for the concrete and reinforcement categories. For the first performance level of the concrete, we use the unconfined material representing the cover in the section. This is set to 4 per mils in the fully operational level for the compressive limit strain. For the other performance levels, we use the confined material and select appropriate limit strains. For the reinforcement, we specify tensile strain limits using the reinforcing steel as a material. These strain limits are loosely based on ASHTO performance levels. We can use the Output tab to generate a user-defined report. Once the analysis is complete, we examine the results. In the moment curvature results, we can see that the ultimate curvature is governed by the steel strains. This ultimate curvature and the yield curvature are the basis for the idealized moment curvature law based on Caltrans. This is the basis to compute the backbone for our work law. Additionally, in the report, we also may see an effective stiffness factor, which is calculated as the ratio between the effective bending stiffness of the section versus the elastic bending stiffness. This factor can be later used in the nonlinear analysis to account for the stiffness degradation due to member damage. We can also see the final moment rotation work law, which will be used for our plastic hinge. This is calculated by multiplying the idealized moment curvature with the corresponding plastic hinge length. The plastic hinge task outputs a work law which can be imported into SOFiSTiK and assigned to the respective beams. For our bridge pier, we assign the Takeda implicit hinge work law at the top and the bottom of the confined columns. Finally, we export the structure and visualize the hinges in the new viewer. In the next video, we'll perform the nonlinear time history analysis. Thank you for your attention.